In the previous section, we had an introduction to the idea of parametric equations. For this section, we will see how to use calculus to find derivatives, integrals, arc lengths, etc. when we have a curve described by parametric equations. So remember that parametric equations are curves where x and y are each functions of a third variable, which is called the parameter. So x and y are independent of each other, but they're both functions of t, which we call the parameter. Now, when we have a curve defined parametrically, we want to still find derivatives, areas, arc lengths, all these things. So let's imagine that we have some parametric equations. We have an x equation in terms of t and a y function in terms of t. And we want to figure out how can we calculate derivatives, how can we find areas under curves, arc lengths, and surface areas. So let's start by thinking about derivatives. We can express a derivative as dy dx, and we're thinking both of y and x now as functions of a third variable t. So I'm going to do something that might seem a little bit strange here. I'm going to divide both the numerator and the denominator by the same expression. And if I divide numerator and denominator by the same expression, I don't change the value. So I'm going to divide by dt. I'm being a little bit sloppy with the notation here. Technically speaking, we should be more rigorous to really prove this. This is a bit hand-wavy, but it will give us a good intuitive idea of what's going on. So we have dy over dt divided by dx over dt. Now dy dt is the derivative of the y function. We could write this also as y prime of t. So we have y prime of t divided by x prime of t. This expression is now in terms of t, and it will give us the derivative, the rate of change of y with respect to x, in terms of t. So the derivative, we could think of either as dy dt over dx dt, or we could think of it as the derivative of the y function over the derivative of the x function. These are equivalent, just written in a couple different forms. Now let's take a look at finding integrals when we have a parametrically defined curve. So we're imagining that the parameter here, t, ranges between values alpha and beta to trace out the curve once from x equals a to x equals b. Let's imagine here that we're wanting to find the area under the curve from a to b, and we'll draw a picture. So we have the y-axis here, we have the x-axis, we have some curve that's defined parametrically where we have an x function x of t and a y function y of t. We want to find the area under this curve from some value x equals a to x equals b. So we're trying to find what is the area under this curve. We could write this as the integral under y from x equals a to x equals b. So this definite integral is the area under the curve. But we want to express this in terms of our parametric equations. So we're imagining that the parameter t ranges from alpha to beta to sketch out this curve once. So to get this portion of the curve, the parameter t starts at alpha and then it ends at beta. And it's important that we're only sketching out the curve once. We saw some examples of the circle in particular where the curve continued to be sketched out as we varied the parameter, but we only want one tracing out of this curve from alpha to beta. How do we write this integral in terms of the parametric functions? Well, let's take a couple steps to do this. We have the integral of y dx from x equals a to x equals b. Y we can think of as the function y of t. And then ultimately we're going to be integrating with respect to t. So we'll add alpha and beta as the limits of integration. And then we'll think of y here as the expression in terms of t. So we have the expression for y in terms of t. Now dx, let's focus on this portion here, the dx. If we think of dx over dt, that's the derivative of the x function with respect to t. And we said that the derivative of the x function with respect to t could just be written as x prime of t. So we can express dx dt as x prime of t. Now I want to solve for dx. So dx equals x prime of t dt. Here's an expression for dx in terms of t, and that will transform our integral from integrating with respect to x to now be in terms of t. So replace the dx with x prime of t dt. So here's our expression for the area under the curve in terms of the parametric equations. We have the y function times the derivative of the x function, and then we integrate between the parameter values that give us the portion of the curve we want. This integral will give us the area under the parametrically defined curve. So filling in the blank here, the integral is from alpha to beta, the y function times the derivative of the x function, integrating with respect to t. Now let's talk about how to find arc length with parametric curves. So we're going to draw a picture here similar to what we had for arc length with regular Cartesian curves. We have some curve here, and this is parametrically defined once again with the x and y functions. And we could think of having an x value a to an x value b. We want to find the length of the curve from a to b. And earlier we've given this the name L. L is the length of this entire curve. Now to sketch out this curve, the parameter t ranges from alpha to beta. That sketches out the curve once. So this is t equals alpha and t equals beta. And we want to figure out what is the arc length of this curve. So we're going to slice it up into thin slices. Let's take a thin slice here. This is a thin slice along the curve. So we'll call this length some small change in L, dl. So just like we did before, we want to zoom in here and explore what's happening for this small portion of the curve. So we have our curve, which is essentially a straight line because we're taking such a small slice. And we're finding the length along the curve, which we're calling dl. And the smaller and smaller we slice, the more the curve will actually be a straight line, so the error will go away. So that length is dl. Now, if we measure along the y height here, along the vertical, this is some small change in y. We'll call that dy. And then we have a small change in x along the horizontal. We'll call that dx. And we can express dl in terms of dy and dx. We have a right triangle here, so we can use the Pythagorean theorem to write dl equals the square root of dx squared plus dy squared. We had a very similar expression when we were looking at the arc length integral back in a previous section. Now we want to write dl in terms of t. We want to be integrating with respect to the parameter t. So what we're going to do here is multiply and divide by dt. And this seems a little bit bizarre. We saw a similar thing before. And the reason that we'll do this is to transform this expression to be an integral with respect to t. So multiplying and dividing by dt doesn't change the actual expression, so we have not changed the value of dl. We're going to take this 1 over dt and bring it inside the square root. And to bring something inside a square root, we have to square it. So we can write this as the square root of dx squared plus dy squared. All of this times 1 over dt squared, integrating with respect to t. Now we're going to distribute the 1 over dt to both of these terms. So we have the square root of dx squared over dt squared plus dy squared over dt squared, still with the dt at the end. Now, what are these expressions? This is the derivative of the x function, squared. This is the derivative of the y function, squared. So we can write our integral for arc length in terms of the parametric equations as the integral of dl, and now dl is the square root of the x function derivative squared. This is the same as dx dt squared, so we have the x derivative squared, plus the derivative of the y function, also squared. We're integrating with respect to t. T ranges from alpha to beta in order to sketch out this entire arc length, so our limits of integration are from alpha to beta. So this expression gives us the length of the arc using parametric equations. Finally, for surface area, we can use the expression that we developed earlier for the surface area rotating about the x-axis. We'll only worry about rotating about the x-axis for this section. We could do a similar surface area integral for rotating about the y-axis. But if we rotate about the x-axis, we had this integral for the surface area of the resulting shape. Now, we're going to take the same expression for dl that we found for arc length, and the y we're just going to write as the y function. So we can write this integral as the integral of 2 pi times the y function in terms of t, and then dl is the same dl that we just developed here. So dl, once again, is the square root of the x derivative squared plus the derivative of the y function squared, integrating with respect to t. So to get the entire surface area, we integrate from t equals alpha to t equals beta. And here's the integral that gives us the surface area of our parametric curve rotated about the x-axis. If we were rotating about the y-axis, we would simply replace this y function with the x function. That would give us the surface area formula for rotating about the y-axis, but we won't worry about that for this section.